Welcome back everyone. In the last class we had seen what is a standard block diagram or standard configuration of a control system. It looked something like this, where you had a controller, you had a plant and a feedback element. Plant is the system that you want to control. The control variable will be the output. In this case, we want that the output here should follow the reference signal, which is this RT. There is a feedback element whose transfer function is Hs, and we have an error signal Et, which feeds into the controller, and the output of the controller is the input to the plant. This was the basic structure we had discussed in the last class. So, today we go ahead from that point and let us see how to, at the beginning let us see how to make this basic structure or the standard system into a system of one block. Here you can see there are 3 blocks. I will convert this system into a system of one block. Now, for that we will write everything in terms of the Laplace variable. So, here the reference signal RT's Laplace transform is Rs, that of Et is Es, and that of Yt is Ys. Okay. So, then the question that we are asking is, how can I replace this system with a single block of this form? So, where the input would be Rs and the output would be Ys. So, in other words, I am asking the question, what is the transfer function of the system which relates Ys to Rs, or what is Ys by Rs. So, let us try to see what that is, and for that we will first look into a system which does not have a controller in it. We will remove this controller for the time being. So, and then we will see what will be the transfer function of the closed loop system. So, I have removed Ks. So, now let us try to find out Ys by Rs. Now, you notice that Ys here is the output of Gs and the input to Gs is Es. Remember, we are looking at a system without a controller now. So, the input in this case is Es. So, from here we can directly write that the output Ys must be equal to Gs by Es, because Ys by Es must be equal to Gs, right. This is what we know for LTI systems, this is true. So, now what is Es? Es is the signal Rs minus the signal that is at this point. Now, what is the signal at this point? That is nothing but the signal that is coming in from here multiplied by Hs is the output or the signal at this point. So, that is what we are going to write now. So, we will replace Es by Rs minus Hs Ys. You see, Ys is the input to this Hs. So, the output here is Hs Ys, right. So, therefore, Rs minus Hs Ys is Es. So, we are replacing Es with that. So, again remember what we are trying to do, we are trying to find out. So, what we are trying to do, let me just write down Ys by Rs. We are trying to find out what this is. Okay. This is our destination for this derivation. Okay. So, here what we will do is we will take the Ys terms on the left. So, here you see this term Hy into G, I take on the to the left, and if I take Ys common, I am left with this, and now you see I just have to do Ys by Rs, and that will be given by this expression. So, that means the transfer function relating the output Ys to the reference Rs is nothing but Gs by 1 plus Gh. Now, notice here something, I have used a negative sign here. So, this is a negative feedback configuration. Remember, in the last class I had showed that you can have positive and negative both. So, now what I have done is for this class or for this derivation, I have considered this to be negative. So, if it is negative, you can see that this is Gs by 1 plus G into H. So, basically what I have done is I have removed these blocks and converted them into one block. So, this is the closed loop transfer function of this system. Because it is a closed loop system, I have combined everything together and made it into one single transfer function, that is Gs by 1 plus G into H. What if we have positive feedback here, that means we have a positive sign here, then Es will become Rs plus Hys, instead of Rs minus Hys, it will become Rs plus Hys, and then there will be a sign change here. So, you can see that for a positive feedback term, we have G by 1 minus Gh, whereas for a negative feedback term, we have G by 1 plus Gh. So, as a whole, for a negative feedback configuration, the overall transfer function of this closed loop system, this is how we say the overall transfer function of this closed loop system, that means Ys by Rs is nothing by G by 1 plus Gh, and for the positive feedback configuration, the overall transfer function is G by 1 minus Gh. Okay. Now, I bring in the controller. Remember, I had removed the controller just to make our derivation simpler. So, now I bring in the controller. So, the controller is Ks. Okay. So, now I am asking the question, what is the overall transfer function of this system, of this negative feedback configuration system? Why negative feedback configuration? You can see that there is a negative feedback here, there is a minus sign here. So, you can see if I can somehow convert these two together into one block, then I can use the previous formula and find out the value. And what is this? See, let me just call this point, the signal at this point, let me call it suppose Ps. Okay. So, then we know that you see Ps by Es must be equal to Ks, right. That has to be followed. So, that means you see Ps equal to Ks into Es. Okay. Now, what is Ys again? See, Ys by Ps is nothing but Gs, and from here we can have Ys equal to Gs into Ps. But from the previous expression here, we know that Ps is nothing but Gs into Ks into Es. So, therefore, Ys by Es will be equal to Gs into Ks, right. So, this is the overall transfer function of the system. Okay. I can replace, see, let me just remove these and write it down here for our easy reference. So, let me just write it down here. What we have got is Ys by Es is nothing but Gs into Ks. So, I will just remove all this and clean it up a bit. Okay. So, now which means you see this entire thing is Ks into Gs, right. This is Ys by S. So, I can replace this entire block by Ks into Gs or Gs into Ks, with whichever way we want to write. So, in that case, if I just use the formula, remember the formula was G by 1 plus Gh. I am not writing the Laplace variable again, just to avoid writing it every time. So, G by 1 plus Gh was the closed loop transfer function. Now, in this case, G will get replaced by K into G. You see, that is the only difference. Okay. In the same way, for the positive feedback case also, it was G by 1 minus Gh, but now G is, you have a new G, the new G is K into G. So, that new G I am writing, so that is Kg by 1 minus Kgh. Now that we know all this, okay, so basically now we know how to convert this standard system into one block of transfer function. So, now we go ahead and try to see how does some special systems, some important systems behave. So, first of all, we will take one of the most simplest cases where we will consider. So, we are working only for negative feedback configuration here, because we know that for the positive feedback we just have to take a minus in the denominator. So, I will not show the positive feedback case. If required, we will, you can do that on your own. So, now what I want to do is I am saying that suppose Gs is 1 by St and Hs is 1. So, in that case, this is the closed loop system block diagram. Okay. These are called block diagram because I am drawing it with blocks, right. So, that is why it is called block diagram. Of course, I mean the name itself should tell you what these are. So, So, now let us try to find out what is Ys by Rs by using the formula. What was the formula? You see, the formula was G by 1 plus Gh. Again, here there is no controller setting over here, Ks is 1. So, we have Y by R equal to G by 1 plus Gh. So, which will come out to be 1 by St, G is 1 by St plus 1 by St multiplied by 1, and we do not need that one. So, finally, the expression will be 1 by T by S plus 1 by T. So, this is the overall transfer function of the system. So, if this is the overall transfer function of the system, where are the poles of the system? The poles of the system are located at the roots of the denominator. The roots of the denominator in this case are at minus 1 by T, because S plus 1 by T by 0 gives you S equal to minus 1 by T, right, the roots of the denominator. Okay. And the numerator, there is no polynomial in S, so there are no zeros. So, zeros, there are no zeros of the system. Okay. Now, this is a standard first order transfer function. Why is it called a first order transfer function? Because you see in the numerator, the degree of the polynomial is 1. So, the what is order of a system? Order of a system, order of a system is the degree of the denominator of the transfer function. How does this system behave when I give a step input to this system? Okay. So, let us see. This will help us understand the system better. That is why we will give a unit step input to the system. So, let us try to find out the unit step response of the system, and you know how to find out the unit step response of a system. So, that is nothing but, we have done this type of an example. So, Ys is nothing but 1 by T by S plus 1 by T into Rs. Since we are trying to find out the unit step response of the system, so first question is, what is the input of the system? The input of the system is unit step. So, if you have a unit step input, so these are okay. So, you know what is Rs? Rs is equal to 1 by S. We have talked about this earlier. So, Rs will be replaced by 1 by S. Now, we will have to write down the partial fraction for this, and the partial fraction for this will be something like this: 1 by S minus 1 by S plus 1 by T. This will be the partial fraction. So, what will be Yt? Yt will be Laplace inverse of 1 by S by 1 by S plus 1 by T. We know how to find out these. We have seen this earlier also, how to find out step response of a system. So, 1 by S Laplace inverse is 1, and the Laplace inverse of 1 by S plus 1 by T is e to the power of minus T by T whole into u step. Okay. Because what was the Laplace inverse of 1 by S? The Laplace inverse of 1 by is nothing but unit step, right? And what was the Laplace inverse of 1 by S plus A? It was nothing but e to the power of minus at u step, right? I have used these two formulas to find out this. So, Yt comes out to be this. So, if Yt comes up to be this, so these are the transfer function and this is our step response. So, in that case, you see, if I go ahead and plot from t equal to 0 to t equal to 10, okay, this is a plot of the output. So, this side is Yt and this side is your time t. So, for t equal to 0 to 10, this is the blue line is the output. Okay. Now, think from a control system perspective. What are we trying to do in this system? We are giving a reference signal. The reference signal here is a unit step signal. So, a unit step signal will look something like this, right? It is a unit step signal. We are giving a unit step signal. This is 1. So, basically what we want is that the output should reach to this value, right? Because that is the reference, that is where we want to reach, that is the desired point to which we want to reach. So, we want that the output should reach to this point, and if you see the plot, Yt is actually reaching to this red line which is 1. Okay. So, in this case you can see that the step response reaches this. This can also be shown mathematically. So, how do I show this mathematically? You think about it. How do I show this mathematically. What I am asking is, so the reference signal is unit step input, so that means I want my output to reach the reference signal, right? And then I should check what is the final value of the output signal, finally where is it reaching, but we know how to find out final value, right? Final value of any signal, how do we find out? Limit of t tending to infinity that signal, right? So we can find out the steady state value of the output, which is also called the final value in other words. So that is limit of t tends to infinity y of t, that is limit of t tends to infinity y of t is this. So you can see that this will come out to be 1. Why? Because limit of t tending to infinity 1 u step is 1 and limit of t tending to infinity this term is 0, because here 1 by t, although I have not said that, is greater than 0. Okay, we are assuming it to be greater than 0. If t was less than 0, then e to the power of minus t by t, that minus and the negative, since t will be negative, then those will cancel out and you get a positive exponent, e to the power of a positive number, which means it will blow up as t tends to infinity. But in this case t is greater than 0, t is a positive number in this case. So which means that limit of t tending to infinity y of t is 1, which is exactly what we are seeing. You see, this is reaching 1 as y is as time is increasing. Okay, we can also find out what will be the error. Okay, now before that, let's think about it. Okay, from an engineering perspective, you have a system. So the plant came out to be the 1 by st. The feedback is 1 in this case. We have not added a controller yet, and the standard control feedback control system or the feedback control block is the one that is shown in this diagram. In this diagram, whatever is shown, this is the standard block. As an engineer, what are you trying to do? You want that the output should reach the reference, and the reference you have given as 1, say in this example, right? We have taken unit step input. So I want that my output should reach to 1. Now what we can see is that as limit t tends to infinity, it goes to 1. That means, think about it from an engineering perspective. It means that you will have to wait till time t tending to infinity so that the output goes to 1. That doesn't make sense, right? Why will you wait to t tending to infinity? That's not possible also. What is the meaning of infinity here? So physically or practically, if you have this type of a system, what we do is we do not wait till t tending to infinity. Instead, we say that whenever the input had reached to certain band, okay, maybe 99% of the final value, we say that we have reached the desired reference point. Okay, so that is what is being shown in this diagram. So we say that, say suppose, although exactly it is not visible, so suppose this is 0.98. Okay, so we are saying that as soon as the plot or the output crosses 0.98 and it does not come out from that band, we will say that we have settled. We have settled to the reference point, and the point at which it reaches that, we call that settling time. Okay. Now of course this is a design thing. How much of band you can allow, that depends on what type of application you are working with. Okay, someone might allow 95%. For example, although the example of a drone does not fit in here because it is a drone, you know that at least in case of the z direction, we have seen that the transfer function is 1 by s square. So I cannot, it is not a first order system. If this was a quadrotor, it is not 1 by st, it is 1 by s square. So it doesn't fit in directly. But suppose you had a first order sum system and you had to reach some point, we can always say up to what much you can, what is the tolerance that you can keep. Okay. So now what we will see is what is the error. Okay, what is the error means, how is the error behaving. Remember, we want that this error signal should go to 0, then only your Rs and Ys becomes equal, right, because there is no feedback point here. Okay. There is no transfer function sitting over here. So Ys and Rs is equal only when Es is 0. So let us see how does Et behave. Et is the Laplace inverse of Es. So the error signal is Rt minus Yt, and we already know what Yt is. We have found out from here, and then the expression will come out to be e to the power of minus t by capital T. Now if you find out the steady state value or the final value of this signal, you see that it will come out to be 0. That means at t tending to infinity the error becomes 0, which means that the reference and the output are the same. Okay. So, what I want to show now is that you see all these are fine, okay, but the expression y t here depends on what? It depends on 1 by t, the term 1 by t, and that is very important. What was 1 by t? 1 by t minus 1 by t are the poles of the system, remember, just by finding out the roots of the denominator. So, this 1 by t is the term which is very important. Okay. So, what we will do now, we will see a simulation where what we will do is we will say that the transfer function ys by rs is equal to p by s plus p. So, basically p is equal to 1 by t. Okay. So, I will vary p and see what the effect of varying p is. Okay. So, let us see. So, remember, suppose the example that I have taken, maybe you can take something else also. If I start with 2 by s plus 2 say, then where is the pole of the system? Pole is a complex number, so we can draw it on the complex plane, right. So, if this is the real line and this is the imaginary line, the pole of the system, suppose it at minus 2. Now, what I can do is I can change p to 3, which means I am bringing the pole to the left, I am bringing it away from the imaginary axis. So, as I increase the value of p, I am basically moving away from the imaginary axis. Let us see what is the effect of that. So, I mean, I am not going into the code is there. So, you see p by 1 plus p. So, I will explain how to write down transfer functions and all later. Let us just quickly look at the plot. So, here is the plot, right. This is exactly the response that I had shown you. So, you see this is for p equal to 1. Now, as I increase the slider, the p value changes. So, this is p equal to 2.33, that means I am moving away from the imaginary axis, remember. So, as I increase p, I am moving away from the imaginary axis, and you can see that the response is getting faster and faster. What do you mean by faster? That means that the step response is going to the reference quicker and quicker. It is going much faster now. Okay. So, as the pole of the system moves away from the imaginary axis, the response of the system, of this first order system, is much faster. Okay. So, this is how poles affect your system's response. So, in other words, if you can control the pole position somehow, you can control the response also somehow. When I am using the word control, do not think of control systems. I mean, let us use the word manipulate. Okay. If I can manipulate the pole p here and the position of the pole p, then I can manipulate the system's response as well. Okay. So, keep this in mind. This is a very important point, and I will come back to this point in the next class. Okay. So, today what we have seen is how does the pole play a role in the response of the first order response or the step response of the system. The same thing can be done with ramp response also. I will take it up in the next lecture, but for today's lecture we will end it here, and from the next lecture we will look at ramp response and also see how does the pole play a role in the response of the system, not only for first order but also for second order. Thank you.